The image here is a famous one in which we have a glass with an index card and a coin on top. The hand here indicates the pulling or removing of that card very, very quickly. We can see afterward what happens is when we remove the card very quickly, the coin, instead of traveling with the card, drops into the tumbler. This phenomenon, a famous one, not only with glasses and tumblers, but performed by magicians and dining room tables, pulling the dining room table cover very quickly from the table and leaving the dishes and plates and cups and so forth in place, can best be explained by concepts of inertia, momentum, and change in momentum, especially inertia. Another example of inertia in operation is this picture of this motorcycle rider right here. You can see the motorcycle had been riding very quickly and collided with this wall. But upon impact with the wall, we can see that the rider continued to move forward because the rider had inertia moving forward. So what is inertia and what causes all these different types of motions? That's the subject of our major unit, momentum, and its conservation in our first lesson on inertia, momentum, and change in momentum. So, on our introduction to momentum, its conservation, and Newton's laws, I want us to situate us a little bit broader in the course. Up until now, we've been studying and addressing the question, how do objects move? That's the field of study called kinematics. It is largely descriptive. So we might study how an object is moving along a road at constant speed. And we would use equations like average velocity is distance over time, or velocity equals at plus v0, or x equals 1/2 at squared plus v0t plus xo. We might examine an object that is speeding up or accelerating using the same equations. All of these equations allow us to answer the question, how do these objects move? How are they moving? We're describing that motion, just as we can drop an object and watch it free fall and study its motion, or we could throw the object up in the air and observe its motion. We can predict its motion, we can describe its motion in terms of the velocity, acceleration, and we can even get sophisticated, as we ended up, where we would have an object, a projectile, fired or kicked or thrown at some angle, and we could predict its path, its time in the air, and so forth. But all of this is descriptive. That's been the subject of our study so far this year. We're now moving into a new field, which is explaining why objects move the way they move. Why do they do the things they do? Why do objects move in the universe the way they do? And this question why is the subject of dynamics. It is causal, whereas kinematics is descriptive, dynamics is causal. It explains the causes. And the sub-questions that it seeks to answer, and we will learn to answer using concepts of physics, is what causes objects to move? What causes them to change their motion? It is one thing for an object to move, but it is another for its motion to change. That suggests something else is going on. Well, what are the concepts that are relevant to the motion of objects? And what are the laws and principles that govern the motions of objects? This is the subject of the field of dynamics. And we will begin this first area of study with a focus on a unit called momentum and its conservation. The first concepts we're going to grapple with are inertia, momentum, and change in momentum. So let us first define what inertia is. Now, as you've heard me say throughout this course, definitions are only as good as the understanding behind the people using them. And anyone at any time should be able to come up with their own definition of a word or a term if they understand what it is. So inertia is an object's ability to resist a change in motion. An object's ability to resist a change in motion. The factor, the only thing that this depends on, and this is not obvious, it only depends on mass. Only mass. What has more inertia? Something with more mass. What has less inertia? Something with less mass. Now, the concept of inertia goes hand in hand with Newton's first law, which says an object in motion tends to stay in motion. An object at rest tends to stay at rest unless acted upon by an outside force. Fundamentally, what this means is objects want to keep their motion. Objects seek to preserve their state of motion. That state can be in motion, moving along in a particular way. It wants to keep that motion. Well, that's what we saw with the motorcycle rider. The motorcycle rider is riding along the motorcycle at 20 or 30 or 40 or 50 miles per hour. The motorcycle stops, but the rider is moving. It wants to keep that motion. So if the motorcycle stops, it is stopped by the wall. This tire wall exerts a force on the motorcycle and stops it. So the motorcycle would want to keep going too, but it's acted on by an outside force, the wall, which brings the motorcycle to a stop. But you can see, because the rider is higher and not physically attached to the motorcycle, when the motorcycle stops, the rider continues to move. It's actually not the case that the rider is thrown. The rider just keeps moving as he or she was doing before the impact. So that's if the object is in motion. It wants to keep that state of motion. What about an object at rest? Well, we can see here with the tumbler, the glass example, the coin is at rest. It wants to stay at rest. So when the card is pulled very rapidly, the coin is able to stay at rest, but now there's nothing holding it up and the coin falls into the glass. So the law of inertia actually accounts for both situations, both states, where an object is moving and when an object is rest. In either case, to change them, there must be an outside force. This is not really intuitive. We tend to think, we have the misconception, that objects to move require forces. That's actually not true. You could do a little thought experiment, like a Denken experiment. If we take a box of tissues and we slide it very quickly across the floor, like throw it parallel to the floor and slide it, that box of tissues will come to a stop. It comes to a stop because of friction. But what it wants to do is keep moving. We can see this if we substitute the box of tissues with a hockey puck. If we do the same thing with a hockey puck, it will come to a stop. But if we remove friction by, say, throwing the puck just as hard on ice, it will go much, much further. Taking this thought experiment further still, if we go into outer space and we throw an object, say at 60 miles per hour, a baseball or something like that, into space, once it leaves our hand, it will travel at that speed in that direction forever until it hits something else. That something else provides a force to change its motion. So the natural state of objects are to preserve their current state of motion. As we'll see when we get near the end, I'll introduce you to Newton's second law, but I'll introduce it here because this relates to changes in motion. Newton's second law, simply stated, is F equals ma. I like to explain it in a little more detail and say it's F net equals ma net. Where the net force is the sum of all the forces. And the net acceleration is the observed acceleration. So in this particular case, let's suppose I have a book sitting on a table. When we look at it, its acceleration is 0. We observe no acceleration when there's a book sitting on the table. That means that the sum of the forces must be 0. If this is 0, this must be 0. We know the book has mass, so this is not 0. Acceleration we observe is 0, so therefore the net force is 0. So that means we have a force of gravity pulling it down. And we also have a force called force normal, which is the table pushing back, which we will talk about in a little more detail. But it's pretty simple to understand that if these forces are balanced, there must be another force acting in the other direction, counteracting gravity. For as soon as we pull the table away, the object will fall, just as it did with the glass and the coin. So what we could see then, back at this card, is the card must be exerting an upward force. Gravity's pulling it downward, and as soon as we remove that upward force, the coin will be subject to gravity and it will fall. So gravity wins. But gravity was acting the entire time. If it weren't acting the entire time, then the coin would be free to move around. So we can see as these two forces are equal and opposite. So if we were to say that this is minus 8 newtons, then this would be plus 8 newtons. And the sum of those would be 0. So observed acceleration, none. The book is sitting on the table. The net force, the sum of those two forces is 0. So the net force 0 is proportional through mass to the observed acceleration. So this is Newton's second law. Another way to say it conceptually is to say that the acceleration observed is directly proportional to the mass, or inversely proportional to the mass. Sometimes we see the formula written this way. Acceleration equals F over m. So the acceleration in this case is inversely proportional to the mass. And of course, as you remember from math, an inverse relationship looks like this. Y equals k over x. X is inversely proportional to y, so in this case, the acceleration is inversely proportional to the mass. So that's inertia. It depends only on the mass. Well, let's look at this a little more closely because this produces an oddity for us. So let's imagine that we have a 100-kilogram asteroid. We have a 100-kilogram asteroid, which I'll depict here, 100 kg. So let's suppose. So let us consider some oddities here, or a question to consider. So let's suppose we have a 100-kilogram asteroid, and it is traveling at 100 kilometers per second. And we have another 100-kilogram asteroid, and is traveling at 10 kilometers per second. The question is, if we have this 100-kilogram asteroid, is it harder to increase it to 101, or is it harder to increase this one to 11? Notice this 100-kilogram is going from 100 to 101, so it's a change of 1 meter per second. This 10 kilometers going to 11. What if we have a 100-kilogram asteroid that's at 0 and we want to change it to 1? So in all three of these cases, we have objects traveling at different speeds. We want to change their speed by 1 meter per second. The answer is it's the same. Naturally, if you were thinking about this, most people will say that it's more difficult to change this 100 kilometers per second to 101. But the fact is that it's just as hard to change all of them by 1. Whether it's moving very quickly, whether it's moving less quickly, or whether it's not moving at all, how difficult it is to change them by 1 meter per second, to increase their speed by 1 meter per second, is the same. Now, how that's important is if we go back to the definition of inertia. An object's ability to resist a change in motion. So all of these three asteroids want to resist their motion. They want to resist a change. And what we said is that inertia depends only on the mass. The only thing that resists the change in motion is the mass. That's the only thing that matters. So in this particular case here, the fact that they're traveling at different speeds makes no difference. Similarly, if we were to ask, what if we were to change its speed so it were only going 99 kilometers per second, or 9 kilometers per second? Or we want to change it in this direction to -1 meters per second. Well, now, based on the last example, you'd probably answer that it's also the same, and that would be true. But again, that's not obvious. We're slowing this down by 1 kilometer per second. We're slowing this down by 1 kilometer per second. And this one, we're changing its speed by 1 meter per second this way. Notice I changed my words because of language, but physically the same exact thing is going on. In this case, I'm going to push on this asteroid enough to change its speed by 1 meter per second. So it's actually slowing down this way, so it's accelerating that way. I'm accelerating it this way. I'm applying a force this way, enough to change its speed 1 kilometer per second. Similarly, in this case, we have it traveling at 10 kilometers per second, and I will apply a force in this direction to change its speed to 9 kilometers per second. So we have a slowing down in this direction, which means it's accelerating that way, to the left, and that requires a force to the left. So this one's changing by 1 because of a force. This is changing by 1 because of a force, and those two forces would be the same. Now this one, not quite as obvious, it's at rest. So to change its speed this way, 1 meter per second, means it's actually going to be going in the opposite direction. But it's 100 kilograms, and I'm going to have to push the same, using the same amount of force that I have to apply in this direction. In this case, the acceleration the change of velocity is 1, change of velocity negative 1 in the second case, and -1 in the third case. So the amounts of change are exactly the same. It's just that they happen to have different speeds. Now again, that may not seem obvious, but if we go back to earlier in the year when we considered frames of reference, and we watched the video of the two old professors, and you'll recall that the one professor was upside down, but we thought he was right side up, and then another person entered the frame, and we couldn't really tell which one was upside down and which one was right side up. Well, then they went on to show that when one of them was standing there on the screen, the other one seemed to be walking by, but when we zoomed out, we saw it was the other way around. Well, here is the point. Depending on your frame of reference, if I am a person floating at the same speed as this asteroid, 100 kilometers per second, at constant speed, one, I don't know I'm moving. I don't know that the asteroid is moving. Relative to me, the asteroid is not moving at all. So, it would appear to be doing exactly what this one is doing. So let me repeat that. If I am traveling through space, so let's suppose we were on the bay of the space shuttle, and the space shuttle launched this asteroid and me at the same speed. We would float through space forever at that constant speed, but we wouldn't know we're moving, except if during that acceleration when they launched us. This is like the example of us being in an airplane. If we go to sleep, we wake up, we might forget that we're actually traveling at 700 miles per hour. We don't feel the motion. So in this case, the asteroid is moving at 100 kilometers per second. We're traveling next to it 100 kilometers per second. So when we look at the asteroid, we think the asteroid is standing still, which is this. Now imagine we have a force meter, which is like a spring, and we watch an outside force squish that spring to slow this down. In this particular case, would we expect that spring to look differently if we were watching this space to change it by 1 meter per second? And the answer is no. We wouldn't expect it to look different. We'd expect it to look the same. Because from this frame of reference, we're traveling at 0, it's traveling at 0. From the frame of reference I described here, even though us on the space shuttle think that the asteroid and we are traveling at 100 kilometers per second. In reality, for the two of us traveling together, we think each of us is traveling at 0 meters per second. So therefore, what we see here will be exactly the same as somebody who is at rest. And it turns out that in the scope of things, from our frame of reference, we have no way of telling in the universe which one of these views is correct. So therefore, what we see must be the same. Wow, that's a big TOK connection there, that we, depending on our frame of reference, can't really tell what's true. No. All we know is what other things are doing relative to us, but we don't know which one is true. And it turns out, in terms of the laws of physics, it doesn't matter. So, the bottom line to recap about this oddity is, it doesn't matter how quickly something's traveling or whether it's at rest. The only thing that determines how difficult it is to change its speed is its mass, not the speed that the object has. So now let's define a new concept for understanding motion, and this concept is linear momentum. Now whenever we have something like this, linear momentum, this linear is an adjective, and it implies two things. First of all, it describes the geometry of the situation. In other words, we're talking about momentum of objects moving in a line, and it turns out all objects do move in a straight line. And if you recall in our discussion of centripetal acceleration, when you take a curved path, then there's a force acting on it. So for this to travel in a straight line, there will be no forces acting on it. There is acceleration is delta v over delta t, and if you remember, velocity is magnitude and direction. So if we change either the magnitude or the direction, there'll be acceleration. So for this to be in a straight line at constant speed, the magnitude's not changing, nor is the direction changing. So this descriptor applies to the geometry. It's motion in a line. It also suggests that there are other types. If someone were to say to you a Bengal tiger versus a Siberian tiger, those are different subspecies of tiger. They're different types of tiger. So in the same sense, if we say linear momentum, we are suggesting that there are other types of momentum, and it turns out there are. They're beyond the scope of this course, but an example is rotational momentum. We will talk about that conceptually later, but linear momentum is motion in a line. Rotational momentum is rotation that has to do with an object spinning or rotation. So let's introduce the formula here. The formula for momentum is P equals mv. So whereas inertia depends only on the mass, momentum depends on the mass and the velocity. If you look up the definition of momentum, what you will find is either this formula or the product of mass and velocity. It's not really very helpful. But if we go back to the history of this concept of momentum, before the concept of momentum was developed, natural philosophers or scientists, physicists at the time, used the word impetus. And the word impetus has a couple related roots. Petera, which means to go to or to seek. It suggests that objects kind of have this inherent direction or path or trajectory it wants to take, and they will do it. That is the impetus that they have. Now, of course, this would make sense if we are considering the rider on the motorcycle. The motorcycle seems to be acting like it has a direction it wants to travel. It's like it's seeking to continue its motion. Similarly, the coin is seeking to continue its motion, which is stationary. So the root of the word to go to or to seek, from Latin, impetus, there is the P, from petera. The Greek, petasthai, to fly. Pteron, to take wing. Pterodactyl, pteranodon, helicopter, all these things relate to flying. And of course, a more poetic way to talk about motion of someone or an object is to speak of it as flying, to give flight to something. And so it's a very poetic way. So in any case, these P is one of the reasons that momentum has P. Not only because of the primary concept impetus, but of course you could see it wouldn't make sense to say that momentum is m equals mv, or even capital M equals mv. It would be very confusing, so that's why we don't do it and we keep it straightforward with the momentum. So now let's talk about the units. The units of mass are kilograms, and the units of velocity are meters per second. So the units of momentum are kilogram meters per second. That's actually how we say it. A little bit later, I will also show you how the units are also Newton seconds. So 1 Newton second equals 1 kilogram meter per second squared. And these units are used interchangeably. Again, we'll see why a little bit later. The next thing I want to speak about is the vector nature of momentum. Momentum is mass times velocity. Velocity is a vector, therefore momentum is a vector. Mass is a scalar. So basically, whatever the velocity is, multiply it by the mass. Mass doesn't change, it doesn't have direction, and we'll get the momentum. Also, velocity has magnitude and direction. So if an object is traveling in a line like this, it has velocity in this direction, which means its momentum is in the same direction. So then momentum is a vector. The next concept is change in momentum. Well, if we have momentum equals mass times velocity, how could we bring about a change in momentum? Well, a change in momentum, delta P, would be brought about by some change of mass and velocity. And I put that in parentheses. There's a change in this quantity. Well, how would I bring out a change in this quantity? I could have a change in the velocity. So this would be an object, a regular object like we think of, speeding up or slowing down. And this is the most common one we'll consider in the course. We could also have a change in mass with constant velocity. We won't be looking at in this course, but this would be the case where an object is giving up mass but staying at the same speed is very difficult example to come up with. The third example would be a case when there is a change in mass and a change in velocity. And this is the case of a rocket. What a rocket does, and we'll study this in greater length, a rocket engine, basically it expels fuel out the back, and the fuel changes momentum, and that causes for a variety of reasons, causes the rocket to go this way. So this would be a case. Rocket is stationary, we start burning fuel, the fuel goes this way, that's a change in momentum that way, and it turns out that it brings about a change in momentum of the rocket that is equal and opposite, and the rocket then will go this way. But we'll study that in a little bit greater depth later, further on. So let's do a sample problem. A simple collision with a wall. Very frequently, we will deal with collisions when we're talking about momentum or apply momentum to collisions. Why? Because we are studying changes in motion. A collision with a wall would bring about a change in motion. All right, so I've got this situation, a ball moving west, collides with the wall without a change in the speed. The collision lasted for 0.15 seconds. What's the momentum before, after, change in momentum, and what are the graphs? So this is a case where we have a before-after situation. So I will draw two pictures. I have a before and an after. This is extremely important. Before and afters happen all the time because we're studying a change. So what's the initial, what's the final? It also refers to east and west. So I need to set up my coordinate system. East positive, west negative. And we need a wall. Now the object is traveling westward and hits a wall. So I need the wall to be over on the west side. And we have a ball like this. And the ball is traveling like so. And its speed is 3.2 meters per second, but because this is the negative direction, its velocity is negative. So its initial velocity is minus 3.2 meters per second. collide through the wall and bounce off it without a change in speed. Okay, so again, we have our wall after. We have east and west. And now the ball is traveling this way without a change in speed. So the final velocity, or the instantaneous velocity, is the same speed, 3.2 meters per second, but it's headed in the other direction, so it's now positive. All right, that's very good. And we know the whole collision takes 0.15 seconds. Now, just to help you understand, when it's a ball like this, the ball is going to start out upon impact just touching, and then it's going to start to collapse or squish down. And when it gets to its maximum compression, this would be half the time of impact. And then it's going to, so it's first going to compress, and then it's going to expand. And when it's fully expanded, then it will leave the wall. So that whole time is 0.15 seconds. So it's slowing down, negative 3.2, and then by the time it gets to here, it squeezes this much, it'll be 0, and then it goes from 0 to positive 3.2. So we have 0.15 seconds is that amount of time. So what is the momentum before? What is the momentum after? What's the change? Let's consider and do the graph. So let's there are 4 things we're looking to calculate, so I'll divide my space into 4. I'll first begin with my inventory. I have a mass, which is 0.500 kilograms, and it has 3 significant digits. I have a V0 of negative 3.2 meters per second, and that has 2 significant digits. I have a final velocity of 3.2 meters per second, and that has 2 significant digits. I have a time of 0.15 seconds, which has 2 significant digits. So I want to know the momentum before. So momentum is, change colors here, momentum is mass times velocity. The initial momentum is going to be the mass times the initial velocity. So we have 0.5 times negative 3.2, which is going to be negative 1.6 kilogram meters per second squared. Meters per second. Two answers, 2 significant digits in our answer, because we have 2 here, and even though the mass has 3, this is 2, so the overall. And we have 2 in our answer. So that's our initial momentum. Now we want to know our final momentum. Well, we can use the same inventory, and now we'll have our momentum is mass times velocity, 0.500, and 3.2. So now we have a momentum of 1.6 kilogram meters per second. Notice the only thing different is the directions. The magnitudes are the same, 1.6 kilogram meters per second, and this one's traveling to the west, negative, and to the east, positive. So this is one way we can do this problem. We calculate the before, we calculate the after. I'm going to show you a little bit faster way to do this. And that is simply, we know the change in momentum is due to the mass times the change in velocity. Well, the mass is 0.5, and the final velocity is 3.2, final minus initial minus a negative 3.2. So now we have 0.5 times 6.4, or the change in momentum is 3.2 kilogram meters per second. Notice the sign of this answer is positive. So let's see if that makes sense. Well, for this momentum, on the way here as it's compressing, it's going to come to a velocity of 0. So what's actually happening is it's slowing down and comes to a stop. Well, the change is in the positive direction, just like the velocity change is in the positive direction. So that means the force is acting in the positive way. So the change in momentum is positive, and it goes from minus 3.2 to 0. So the change from here to stop is positive 3.2. Then from here to here, excuse me, is positive 1.6 kilogram meters per second. The speed changes by positive 3.2. Similarly here, the velocity changes by positive 3.2. So there's now another change in momentum in this direction. That is another 1.6, which gives us a total of 3.2 kilogram meters per second. That is the change in momentum. Now this one, if we had done our inventory, it allows one step. So it can save work as opposed to doing both steps. The last thing we're asked to find is the momentum time graph. So the momentum time graph time and momentum. The first thing is, what can we read? Well, we can read momentum and time. The gradient is delta P over delta T, which is something actually very important. We don't know what it is yet. But in any case, it's kilogram meters per second, or kilogram meters per second squared. So if we look at this, we could say, oh yeah, this is kilogram meters per second is mass times velocity. Kilogram meters per second squared, we could see this is mass, and this is acceleration. Now previously, I told you that the definition of Newton's second law is F equals ma. So we've got kilogram meter per second squared. We then see that the slope is, or the gradient is, force. And the area would be momentum times time, which would be kilogram meters per second times seconds, or kilogram meters. The area tells us nothing. All right, so now let's imagine time 0. Let's go back to the graph, constructing the graph. At time 0, in the beginning, we had some momentum. And the initial momentum we said was minus 1.6. So we have this initial momentum, which is minus 1.6. And it's traveling along. And then it makes the initial contact with the wall. And after some time, 0.15 seconds, 0.15 seconds, the momentum ends up being positive 1.6. So there is some kind of change in the momentum here that occurs. Okay? And what's not obvious to you, and you don't need to be able to unpack this for Regents, is that the force in between here looks like this. It looks like that. Sigmoidal. And the short answer for that is, if we've got this ball, and it's kind of easy to compress it this amount, and then it's harder to compress it more, and it's harder to compress it more. So we can see here, if the gradient is the force, which we said it is, notice the gradient is small, and then the gradient gets higher, and it reaches a maximum, and then it's going to decrease as it expands. So the gradient will actually increase, then decrease, and that's what that shows. But in any case, this is what the momentum time graph would be, and here's our exercise in RGA. The last thing I want us to do is to apply our drawing of vectors to the change in momentum. Change in momentum. Start out algebraically, P minus P0. So in this case, we started out with our picture showed us starting out with momentum. So this is P0. And then later, we had momentum like this, which is P. So then what does delta P look like? Delta P is P minus P0. So we draw P first. So here's P minus P0. Well, plus P0 would be like this. Minus P0 is this. It is the opposite direction. It's P0 inverted the other direction. So minus P0, we would put at the very end like this. And we knew that this one was 1.6, and this would be a negative of negative 1.6, which gives an overall resultant of delta P equals 3.2 kilogram meters per second. And that's what we found when we did this algebraically. So in short, today in this lesson, we defined inertia. We saw some examples where it depends only on the mass. We defined Newton's law as it relates to inertia and momentum. I exposed you to Newton's second law, which we're going to do more with, but it's going to increasingly come up as we study momentum. We defined linear momentum, the formula and its units. We explored the vector nature of momentum. We saw that there are multiple ways to bring about a change in momentum by changing mass or velocity or combinations of mass and velocity. We studied a very common example of a collision with a wall, exploring the momentum, the change in momentum, multiple ways to calculate the change in momentum, and an in-depth analysis of a momentum time graph. Lastly, we studied that example using vector diagrams, starting with the algebra and then constructing the vectors to produce the resultant. All of this, of course, was part of us addressing our new unit, which is a shift from our study of how objects move to why they move. What causes objects to move? Well, they want to preserve their normal state of motion. What causes them to change their motion? Forces. What are the concepts that are relevant to the motion of objects? So far, those concepts are inertia, momentum, change in momentum, and force. And what are the laws in principle that govern? So far, we have Newton's first law and Newton's second law. We're going to learn more in the following upcoming lectures.